ठीक है वो।
हेलो माइक चेक।
I welcome one and all, both from YouTube and to the audience here inside the lecture theater. Thank you for joining us for this week's Wednesday Colloquium, and I'm extremely happy to host one of the leading physicists in the country. Happens to be from TIFR, Professor Mandar Deshmukh. And he's kindly agreed to give today's colloquium and on a very relevant topic that many of us are interested in. So, thank you, Mandar. Just before I sort of let Mandar take the floor, I'd like to give a little bit of a introduction to Mandar. Mandar actually is one of the first batches, maybe the earlier batches in engineering physics program at IIT Bombay. And this program had lots of sort of interesting ideologies behind it. And he is one of the, sterling, examples of what that program has produced. He finished his bachelor's BTech degree from IIT Bombay in 1996 and then moved on to do his PhD from Cornell University in physics department with Professor TC Ralph. And then before joining TIFR in 2006, he did 3 to 4 year postdoc at Harvard with Hong Kong Park. Both these degrees and the postdoc has led him to sort of think about physics from a mesoscale as well as nanoscale. And this is where I think Mandar's real sort of strength lies in understanding the sort of how to build a technology most relevant to quantum technologies from the design from the nanoscale upwards and also to understand the exotic physics in it. So Mandar, I welcome you. Just wanted to say that, of course, Mandar recently has been awarded the JC Bose Fellowship, and he has been a Shanti Swarup Bhatnagar awardee previously. So, Mandar.
Yes. Okay, yeah, I think this sounds like it's working. Okay, so I'm really happy to be here talking about some of our recent experiments with high temperature superconductors. And I'm going to give you a flavor of this is sort of an ongoing set of experiments. And I'll tell you about what we have accomplished thus far. Some of the details of our gory details, if you're naturally interested, are in these papers, but you're welcome to ask me, and I'm happy to answer them, answer your questions. So let me get started, which is with the acknowledgements, people who actually do the hard work, who make this work possible, and allow me to give a talk on their behalf. So my PhD student Sanat Ghosh led most of the work on these high temperature superconductors, something that he actually fleshed out in his PhD. Before that, it was a kind of a project for an undergraduate student, and he took it to a much higher level over the 6 years that he was here. Now he's a postdoc at Columbia. Then Vilas was a postdoc. Amit is a PhD student who is leading this sort of project. And there are many people who came together as a team and made this work. I'll try to give you a flavor for why this system is a little bit experimentally very challenging as I go along, but it will never do justice to the actual difficulty of working with this material, but I'll try to give you a flavor. So there are two JRFs, Kuldeep, Achintya, who have contributed. Digambar is a scientific staff. Neha is a JRF. Khushbu was a postdoc and contributed to this project. And sort of my sort of collaborator in this experiments is Professor Tamilvel and his scientific staff, Ruta. So this is very critical because this material requires to understand the physics and to take it to a level of devices, you need good quality materials, and he has played a very kind of important role. There are very few people in the world who actually grow crystals and in BISCO, and so his group's sort of collaboration has been very important. And then we also collaborate with theorists to understand some of our physics. So Felix von Oppen at Free University of Berlin has helped us understand a lot of aspects about this Josephson diode behavior that I'll talk about. And I'm grateful to have scientific staff, Santosh and Sriram, who kind of help in overall getting our experiments sort of positioned for and happen on a kind of day-to-day basis. So I'm going to quickly flash what we do in general. Our lab tries to look at essentially electrical properties of variety of systems, starting with quantum transport of Moiré systems, which is twisted layers of 2D materials, graphene. And we also work with mechanics, although less so than we did earlier, but we have some ongoing experiments coupling mechanics to the physics of topology of 2D materials. And we have a small but consistent effort looking at magnetism in 2D systems. And something that's I will spend a lot of time talking about is devices and physics coming out of high temperature superconductors down to a few unit cells limit. And this connects to another broad area, which is physics of Josephson junctions, which we also study extensively Josephson junctions using graphene and using them as amplifiers and quantum sensors. But for today, I'm going to restrict myself and talk about this sub aspect of our work and try to give you a bird's eye view with some details. But because of the nature of the colloquium, I won't cover all details. If you have any questions, please do ask. But if it's super technical, maybe you can catch me at the end of the talk so that I can finish what I intend for today. So this is roughly my outline for today's talk. I'm going to give you an idea about high temperature superconductors. Then a particular creature in that zoo is this acronym BISCO, which you'll hear me say. It's a bismuth strontium calcium copper oxide. It's colloquially just referred to as BISCO. That's one creature in that zoo of high temperature superconductors. And it's really convenient for us because it's a material that you can peel off down to a single unit cell. With that, I will sort of go into sort of this idea of how you can make detectors, photodetectors, using this material, particularly small wires of it, and where we would like to take this further. Then I'll segue into Josephson junctions, which many of you probably have heard of, but I'm going to give you a pictorial introduction to Josephson junctions and what makes them interesting. They kind of symbolize sort of the unique property of a superconductor, which is a macroscopic quantum state, and it's reflected in these Josephson junctions. And I'll tell you why they're interesting. And a particular version of it is what the community calls a Josephson diode. And I'll demystify the jargon and explain to you what is interesting and what's new and what we don't understand. And I'll end with sort of one or two slides of why, what's interesting, what can we look forward to in the future. Okay, so let me get started with the broad introduction. So high temperature superconductors have been around for a long time, many decades now. People have understood the experimental phenomenology of it, but many aspects of high temperature superconductivity are still not, or microscopic understanding still eludes us. it's an outstanding puzzle in condensed matter physics. But what people agree on is that the origin of high temperature superconducting state arises from this peculiar antiferromagnets in copper oxygen lattice. So I'll show you a 3D version of it. So you have a copper oxygen plane which forms this square lattice, and there have antiferromagnetically aligned states, and at sort of parent state, it's an antiferromagnetic with insulator with no availability for electrons to hop from one side to another, and which is a peculiar state for sort of a mother state from which the superconductivity to arise, because you have seemingly an insulator, but there are now other experiments where in systems like Moire, twisted graphene, where they are providing some insight, maybe not directly connected to what could be the origin of this superconductivity, but that's for some other day. So the phase diagram of high temperature superconductors is very complex. It has variations from one family to another family, but there is some common features that you have this superconductor. Then you have an antiferromagnet, which is very close to it. And you can get a huge amount of variation in superconducting transition temperature by changing the chemistry of this compounds. And that's sort of the main material that we use. So it's a very complex crystal. This is one unit cell of the material that I referred to throughout this talk called BISCO. It's bismuth, strontium, calcium, copper oxide. And this you'll see in oxygen, there's 8 plus delta. Okay, so the delta tells you that if as you vary this off-stoichiometric doping, you will tune the superconducting properties, and it gives rise to lots of interesting physics. Let me also say that this particular material is the heart of the superconductor. Is this copper oxygen? Okay, yeah, these orange and green layers, copper oxygen planes. It's the superconductivity kind of lives there. And all the other oxide layers are sort of providing some charge to this superconducting layer. But for the purposes of this talk, the rest of the layers act like insulators. They only allow electrons to kind of quantum mechanically tunnel from one set of planes of copper oxide to another. So these are, as I will show you experiments, these are strictly 2D superconductors down to single copper oxide plane. Their superconductivity is that of bulk. Okay, so this is sort of what I was saying, that superconductivity resides in these copper oxide planes, and the rest of the material kind of acts like an insulator. So we don't know a lot of things about the microscopic mechanism, but what we understand, and everybody agrees in the community, is that there is a superconducting gap, which is large. It has a TC of about 85 Kelvin above liquid nitrogen. And its coherence length is very short, which is typical of these type 2 superconductors. The distinguishing feature of these, many of these high TC, okay, if this thing would move, yeah, is this a symmetry of the superconducting order parameter. So I told you one of the properties of a superconductor is that the electrons pair up and form these Cooper pairs. But these Cooper pairs throughout the superconductors are kind of in a macroscopic quantum mechanical state where there is a phase which is universal throughout that superconductor. Now that the order parameter has a D-wave symmetry, okay, which is unlike the superconductors that we commonly know, the low TC one, which has a symmetry which is S wave, which is isotropic in space, in these materials, the order parameter is D wave. So along some directions, there's a node in the gap, and the overall symmetry is D wave, and the complex order parameter is written like this. And this will be important for today's talk, that it's not isotropic, that it's has these nodes will be kind of important in this talk as I go along. So this phenomenology I kind of already explained. There is a superconducting dome. As you tune delta in the copper oxygen planes, it will change TC. So this brings me to sort of one of the challenges of working with this particular variety of high TC superconductor BISCO is that this oxygen wants to leak out of these copper oxygen layers, and it will quickly degrade into a material which is not the same TC before you started doing these experiments. So within a matter of a couple of hours, if you have a very thin layer, this material degrades very rapidly. So you have to take some exceptional measures to make devices very quickly and cool them down to temperatures below 200 Kelvin. Once it's below 200 Kelvin, this mobility of oxygen diffusing out from the layers is kind of very slow or stopped completely. So then you can measure devices for months at a stretch and there's no problem. But at ambient, at room temperature, these oxygen becomes off-stoichiometric very quickly, and you have to work hard to while you're making devices, and I'll point out as we go along. So I'll show you an experiment which very nicely shows that as you tune the oxygen doping, you can basically map out this whole dome. This is done by another group. So that's sort of surface itself, in the sense that the surface atoms are probably the first where off-stoichiometry sort of material exists. But as such, the surface isn't very special. In a way, the surface will come in when I talk of two layers of biscoat which are twisted relative to each other. Maybe I don't know if that's what you mean, but surface itself isn't important only in the context that it is the one that can degrade fastest.
Because any vacancies on the surface, like oxygen vacancies.
Yeah.
That can
in that sense, yes. It can play, I would say, detrimental role to your device and trying to get reproducible results. So you have to be careful about that, and we have spent months. So this material is complicated, but it's of interest. There are other high TC materials from this family, not BISCO, but some other sort of cute sounding names like YIBCO, but they are more robust against this oxygen leakage problem. But they don't have this low van der Waals energy that you can peel them off down to unit cell. They act more like 3D materials. This is inherently a layered material. This is also the material that people have studied the most using STM and RPES in high TC community, because in STM and RPES, when you do the studies, you want to expose a fresh crystal surface, and it's easy to cleave it in situ inside STM chambers and RPES systems. Okay, so, but it's also technologically very interesting material, and there is lots of ongoing efforts, and something that we are also interested in is sort of continuous wave generation of terahertz radiation, and it arises very simply because I told you these copper oxide planes, that's where the superconductivity lives. They are 2D superconductor. They are coupled by Josephson coupling between another layer. So you have a network of 2D sheets coupled by Josephson junction, and you can basically get radiation out of these Josephson junctions. I'll talk about Josephson junctions a little bit down the line, but the energies scales are such that in this material that the emission that comes out of this are basically in terahertz, which is a very band which has very few continuous wave sources which can deliver. So there's a fair bit of work. There's also the kind of work that I'll talk about trying to make Josephson junction squids using BISCO, because if you have some Josephson devices which work at liquid nitrogen temperature instead of liquid helium temperature, you can do some things which you can't do otherwise. So it's a challenging but technologically very interesting material. So we often work with thin layers of BISCO and other 2D materials. So the standard method of peeling down to a few layers is to kind of use what is a fancy word for peeling crystals using Scotch tape. It's called mechanical exfoliation. It's basically you put a crystal and you put it between tape and you peel it off many, many times, and you rely on randomness, stochasticity, to find crystals which are the thickness that you desire for your experiments. And when you put it on a substrate, I'll show you some images down the line, you will be able to tell from their color what is their estimated thickness. That's one way to do it. One other way to make very large area crystals of BISCO is to use a method which is essentially using electrostatics to glue a crystal to an ionic glass. So what we do is we start with an ionic glass and then put the bulk crystal of the high temperature superconductor and essentially bias it so that you polarize this ionic glass, and the mobility of this ions in this is very small. So the crystal essentially gets sort of polarized and glued to the glass. And we want necessarily glass because glass is an insulator. So anytime after that, if we make any electrical connections, nothing else is electrically parallel to. So this way you can get very large area crystals which can, from 1 unit cell, few unit cell relatively easily. We use a combination of techniques to thin down to a few unit cell to do these experiments. So these experiments have opened up some new possibilities. So
Mandar, just quickly, these crystals of BISCO that you get, are they commercially available?
No,
or you synthesized it?
Yeah, thanks for giving me the opportunity to repeat. So I sort of explain in the acknowledgement. So these crystals are made by Tamil Vel, and he has expertise on crystals in general, but particularly BISCO. He has so he has helped develop the process which works to make good quality crystals. There actually, if you look at the papers on BISCO, there are very few groups in the world. There's one group in, or 1 or 2 groups in Japan, 1 or 2 in China, and 1 in Brookhaven. And it's great that we can make the mother crystal here thanks to Tamil Vel. So these are, you can buy it, but these are, you can't get very high quality and in the kind of volume that we need. So that's kind of important. So people in the past used to do experiments on these kind of materials by making many, many crystals of slightly different doping. And these kind of experiments with thin layers have allowed us to kind of make kind of a transistor-like geometry to essentially in the same crystal, same disorder configuration, you tune the density. So you have this is not our work, but we have done some similar experiments. This is where you have a same device and you tune essentially a gate electrode, which is a third electrode in a transistor geometry, and you dope it. You essentially tune the density of charge carriers and you get different transition temperatures. This is sort of the benefit of going down to 2D limit, because the screening length can be fought in this limit, whereas in the 3D crystal, the screening, they have a lot of charge carriers, so you can't really apply external potential to tune the number of charge carriers. And people have actually measured the whole phase diagram using a single set of device. So this is the kind of diagram I showed you earlier. People used to make different devices and then map out the phase diagram. But now with a single device, you can tune like a transistor and measure the superconductivity. So that's sort of the benefit of 2D. Even more relatively recent, cool experiment is that this is out of Fudan University in China, where they had the same crystal, but they expose it to ozone, which is essentially tuning that oxygen stoichiometry. And by tuning the oxygen sort of ozone exposure, they can tune through the whole phase diagram in the same device, which is analogous to making a transistor-like geometry. So not just that, they demonstrated that by peeling it down to a single unit cell, that its properties in terms of TC in its spectral behavior is identical to bulk. So people before these experiments surmised that the superconductivity lives in 2 dimensions in this copper oxide plane, but this is the first direct evidence down to unit cell, or some people have also done half unit cell, which is essentially just one copper oxygen plane in the crystal. The superconductivity is as you expect in bulk. So that's a confirmation of what people always imagine would be the case, that you have a superconductivity in these copper oxygen planes, which is Josephson coupled to the upper layers, and it sort of makes it look like globally like a 3D, but it's intrinsically a 2D system. Okay, so these are really kind of exciting and sort of experiments, and they motivated us to kind of get into this field some 8+ years ago. And one of the sort of things that we have recently completed in the last year is trying to make some devices with these high temperature superconductors, because that's one of the advantages of this system. And so there is a lot of interest in single photon detectors for a variety of technological requirements, but particularly in optics. The key distribution sort of that people want to implement in quantum cryptography, for example, uses these kind of single photon SNSPDs detectors. And the reason is that these single photon detectors have very high detection efficiency, low dark rate count, and very low timing jitter. So they are very good. And most of the experiments so far have been done on low temperature superconductors, which are superconductors with TC of, I think, 10 Kelvin or so. So this is, I don't mean to make you read through all this, but what I wanted to point out is that large amount of effort has been on low temperature superconductors, although there is some consistent effort trying to make these devices out of high temperature superconductors. So let me just, if it's for pedagogy, explain how this works. So you have a long windy wire of a superconductor, and then a photon falls on it, and it locally sort of dumps heat into the system. It creates a hot spot. So when the current goes through, it basically has a feedback mechanism. So it enlarges it further. So you basically, that locally, the superconductor goes into a normal state. And if you were monitoring either the resistance or some kinetic inductance of the system, which is a measure of the superconductivity, you would immediately pick out this change in the local state of the system. People have also tried to scale it into trying to make pixels using this architecture to make a camera based on this technology. So naturally, having a low temperature superconductor puts an additional burden on the application of this technology, because you need to have something which cools it down to 4 Kelvin, and that's often quite expensive, and more than expensive, quite bulky. And so people have been over the last several years trying to think that if you make it out of superconductors which don't require 4 Kelvin kind of cooling, then wouldn't it be nice for a variety of applications, and it would be very compact. I'll show you a sort of image of a commercial cooler which is super compact like this and cools to 25 Kelvin, and its power requirements are very small. Yeah.
Wavelength range for detection, is it for all photons within the visible regime,
Yeah.
or what kind of photon?
Yeah, good question. So in principle, it's very broadband because it's essentially a bolometer. So the bolometer detectors, for example, the ones that you might buy from a Thor lab to connect into they're very broadband. In principle, they can certainly go into far into IR and into visible for sure. So they're broadband because they are essentially transferring the energy of the photon into heat, which disrupts the superconductivity locally. So
Does one know how much temperature change happens there?
yeah, so people can estimate it or model it. One of the challenges in sort of nanoscale physics is that this measurement of temperature at a local scale is extremely non-trivial, and at fast time scales it's harder. So there are no reliable probes to spatially measure, but people are coming up with it. So I will have to look at it, but certainly when you have this kind of a transition, and depending on where you position it, you can expect to get several Kelvin kind of change locally. Yeah.
Yeah. So what I want to ask
Is that these things have become already commercial.
Yeah.
And as you said, it depends on the absorption spectrum of whatever you're coating the nanowire with, it will detect. My question is, in principle, how fast can the detection be? Can it be like picosecond resolution, or is there a fundamental limit there?
So let me go back to this chart. It has so the jitter or the reset time, jitter is something like picosecond. Reset time, which is basically one photon to another, is about, let's say, in this table, roughly 10 nanoseconds ish. So I think that's sort of the rough number, but it can improve. So right now, I think I saw at a booth, you can buy this triacooler integrated with a single nanowire photodetector. I think it can set you back by about 2 crores or about 1 crore. So certainly these are commercially available, but they are needed in large quantities with more scalable architecture, like for example, a camera. So people have sort of proposed that you can also use these kind of detectors if they can be made into array for imaging in biological applications. So there is a fair bit of interest. So in these kind of photodetectors, so people have been working with these high temperature superconductors using a route which is basically cutting. You take a high temperature superconductor, and with some beam of either helium ions or focused ion beam of gallium, you try to cut the material. And that actually is, as I already told you, these materials are extremely sensitive to degradation of the oxygen stoichiometry. But that hasn't stopped people from trying to essentially make small wires of high temperature superconductor by cutting it. What we, in our earlier work that Sanad did, was we figured out that there is a kind of an interesting way, once you get it down to sub 20 nanometer thick, we found out that if you, on the top of the superconductor, if you sprinkle some chromium or some titanium, it actually destroys the oxygen stoichiometry locally because these are extremely electronegative elements. So they will essentially react preferentially with oxygen, and then the material underneath is completely off stoichiometric, no longer a superconductor. So we figured out that this can be done down to very small length scales. I'll show you example of it. So you can make these without degrading the superconductor as much as these techniques do. So you can make it quite nicely. So this was sort of our demonstration that if you have here, for example, image. So this is very thin sheet of this high temperature superconductor with electrical connections of gold. And if you put this ribbon of in between, which is of chromium, it basically makes that whole layer of superconductor insulating. And that was a very interesting and serendipitous discovery that we made, that you don't really need to cut it, because these materials are extremely sensitive to oxygen stoichiometry. You sort of like a rangoli, you drop the chromium on top, and that completely disrupts the superconductivity underneath. And that sort of idea is what we have pushed to make these kind of devices. So what we, for demonstration, what we do is we can make 10 micron long or longer. Right now, our limitation is larger sheets of Bisco, but we can make sort of nanowires, check how they respond in terms of the superconductivity, and the critical temperatures are basically something close to 70 Kelvin or higher in devices. So the bulk certainly has a TC comparable to what one expects, but the nanowires are lower, but still their TCs are much larger, that enough that above 4 Kelvin that you can actually technologically use these using coolers which are very compact. So these biasing currents are of the order of, I'll show you in the next slide, I'll show you, these are of the order of hundreds of nanoamp or hundreds of microamp, sorry. But the biasing condition is somewhat at your call on at which temperature you want to operate. So I'll show you. So typical detectors work, you can measure, operate them as transition edge sensors. Then you have limited operability of terms of temperature. You have to position it here at zero bias. And then as the photon lands on it, you basically make an excursion in this direction, which is increase in resistance. And then you infer the event. Yeah.
Quick question. The fall off of the TC going from a bulk to the nano, do you have an explanation as to why that is the case? And could you reverse it? For example, for a high-end technology later on, if you were to envision going to nanoscale, how would you think of improving the TC even further? Like, going to room temperature, for example.
For room, but I mean, certainly 85 Kelvin, so for example, you can do these kind of experiments, which we have not done, which is expose it to something like ozone, but this reduction in TC is kind of related to this leaving of oxygen. So subsequently, we have now, I'll show you some processes where we peel off at liquid, at temperatures close to liquid nitrogen temperatures, which exposes a surface which is very protected against the diffusion of oxygen. But it's a challenge for sure. But in the sense that even if one gets to 50 Kelvin, it's not that 77 Kelvin or 80 Kelvin is the target. Goal aspiring both aspiring for, but even if you do at 50 Kelvin, it's a kind of significant benefit. So whereas if you have a biased detector like this, you can with a current, then you can get large range of detectivity. So what we showed is that if I look at the resistive transition of a superconductor and I look at the photovoltage response, then we can actually see it. So these are this is about 20 micron long wire right here. This is sort of through this region. Okay, so this thing has a mind of its own. This is the region of the superconductor. This is where we have sprinkled chrome. This is chrome. And we are now imaging its reflected light so that we know exactly where the wire is. So we can shine light. We can simultaneously look at reflected light. And we can now measure map out the photo response. And what we see is that the photo response is peaked at this sort of okay, so it's a little bit weird. Right at this point. So this is the region where the hotspot is. So when we shine light at this place at a particular bias, it's extremely sensitive to the light. To the extent that we can get responsivity which are very large and across a relatively broad range of wavelengths. And this is at about 60 Kelvin, which is already pretty good. What we need to improve is in the electronics that we use to amplify the signal and reduce parasitic capacitance so that we can do it as fast as possible. Around this few months after our work, a group at MIT showed essentially devices made by cutting this high temperature superconductor by this focused ion beam. Their devices are similar, but they can only operate up to 25 Kelvin, and they demonstrated single photon detectors. So at least the proof of concept using this idea works at temperatures above 20 Kelvin, which is kind of the reason why now we want to double down and invest more energy in developing some electronics, which will allow us to do things at 60 Kelvin. That's sort of our target. So I wanted to give you a sense for the ease of doing some of these things becomes easier because these kind of mini coolers which have been developed for this terahertz generation and a lot of other cryogenic applications, including space, is these kind of small compact coolers. So unfortunately, the size is not seen here, but these are these weigh around a kg, which is still quite a bit, but this can cool down to about 40 Kelvin, and its dimension is about 13 or 14 centimeters. So it makes it very convenient to take it around. You just need to supply electricity. That's it. So it makes it sort of combining these materials, including the terahertz sources, with these kind of cryocoolers and also detectors, makes it attractive for technological applications. So you don't need to be burdened with a 4K cryostat that you have to carry around.
Sorry, Mandar.
Yeah.
So in this mini cryocooler, there are also windows to put in light.
Yeah. Yeah, I can share you. There are many companies who sell this. They're small, compact, but you know their performance here is at 40 Kelvin. So they don't have huge amount of heat load, but they're pretty. There's a whole slew of them. If you don't want to work, if you want to work away from 4 Kelvin, then the window of possibilities opens up. Okay, so now I'm going to quickly go in the next 15 minutes, try to tell you about the other part of our experiment, which is involving Josephson junctions and this high temperature Josephson diode. So let me give you a quick pictorial introduction to Josephson junction. So we all know that the most common property that we are aware of a macroscopic superconductor is this, the dissipationless zero resistance state, and also you know, the expulsion of the magnetic field from the superconductor. But the microscopic hallmark of the superconducting state is that you have this Cooper pairs that are inside the superconductor, and they all are sort of coordinated into a same macroscopic quantum state of the superconductor. And you know, some of the fundamental questions were asked: what happens when you entrap the superconductor with a thin layer of insulator? And some really amazing sort of theory based on very simple ideas without actually knowing the microscopic mechanism of the superconductivity can be worked out at a graduate school level or undergraduate level quantum mechanics. One version of it is in Feynman lectures, if you like, was worked out by Brian Josephson, which basically says that the wave function, which is sort of representing the quantum state of the two superconductors, has this phase which is associated with the two superconductors and the density of, for example, the Cooper pairs. So this insulator interrupts it, but the Cooper pairs can tunnel from one side to another. So these Josephson junctions are are bedrock of a lot of the kind of quantum technology. They basically, even if you have an insulator in between, you basically get a supercurrent through the tunnel junction. What they work on is a kind of a nonlinear inductor at a device level. And if you have heard Vijay's talk earlier, qubits are all, at least superconducting qubits are based on these nonlinear inductor. So the Josephson junctions are, in general, very interesting. People use them for a wide variety of applications. Amplifiers, qubits, using superconducting technology. The standard of voltage is actually based on Josephson junctions in our SI system of units now. And there are a lot of sensors which are leveraging the extreme sensitivity of these Josephson junctions to external perturbations. And we ourselves work using graphene Josephson junctions in this space, but they're very interesting and very important for lots of interesting applications as well as fundamental science. Yeah. Yeah. Good. Yeah, thanks for asking. So eventually there is a length scale. You can't have the insulator, for example, millimeter size. So you eventually have to rely on sort of overlap of the wave functions decaying. And so the overlap has to be strong enough through the insulator that you can have a Cooper pair tunnel through. So we are talking about order of a nanometer or so. Okay, few angstroms typically, but beyond that, you won't. About a few nanometers, it's really hard. Yeah, so they're actually not very large. I'll come back to it. The spacing between the copper oxygen planes, the whole unit cell that I showed you was 3 nanometers. So between them is about a nanometer and a half. So it's in that ballpark. Oops, sorry. Unknowingly, I have advanced quite a bit. Okay, so what our focus is that we are not interested in this conventional Josephson junctions. We want to leverage these 2D materials which have functionality which doesn't exist in conventional ways of making Josephson junctions based on aluminum superconductors. We want to focus only on them to make new kind of Josephson junction and Josephson devices because they have an extensive library of material properties. So I will refer to one aspect of Josephson junction down the line. So when people try to, this is somewhat technical, but one of the ways to understand the physics of a Josephson junction is to think of an equivalent circuit, something like this, and in Josephson junction in parallel with a capacitor and a resistor. They arise from either the external circuit or internal structure of the Josephson junction. So this cross symbol is the Josephson junction, and when you send current through it, you basically have a Kirchhoff's law. Part of the current goes through the Josephson junction, goes through capacitor and resistor, and you basically get a equation of motion, if you like this, and this is an equation of motion of the phase difference across it. So the important part of a Josephson junction's response is the quantum mechanical phase difference across the Josephson junction. And as you send more current through it, at zero current, you basically have a potential in which the system lives, which is kind of periodic, and the periodicity comes from this important term here, which is called the current phase relation. And as you apply some DC current through it, you basically tilt this potential. It's called the tilted washboard potential. And the system is represented by a sort of a ball at a particular phase. So as long as it's locked in a minima, doesn't move around, it will basically not dissipate. Dissipation is anytime the phase starts to change, you have a phi dot term, rate of change of flux is non-zero or phase is non-zero, you will get dissipation. So as long as it stays in this minima, it's basically a dissipation-less regime of the junction. And as you apply more and more current, eventually you reach a regime where there is no longer a minima, or the system escapes by thermal activation or quantum mechanical tunneling to the other side. And at that moment, you call that the Josephson junction has switched from a dissipation-less or superconducting state to a normal dissipative state. And it's that sort of behavior of the Josephson junction is the stochasticity, that if you switch it many, many times, if you do this, take it from the one minima potential and you tilt it many, many times, it doesn't switch at the same point, because there is this potential and there is a KBT-like term because it's an activated process. Okay, so now let me connect to the thing that I'm going to talk about is Josephson junctions are reciprocal devices, that they don't tell from one electrode and the other electrodes are typically not very different. But there are some conditions under which you can get non-reciprocal charge transport. So let's step back and ask ourselves about the first instance where we can see non-reciprocal transport is sort of a PN junction diode, which many of us have played with. So you have a piece of semiconductor which is p-doped, another which is n-doped. You kind of stick them together, and if you apply one bias voltage and another bias voltage, the current going through the device is not the same. So at a device level, it seems consistent with the band diagram, but fundamentally what's happening is you're breaking inversion symmetry. X transformed to X, minus X, you're breaking, it's no longer the same. So the symmetry that's being broken is inversion symmetry. So that's at the heart of this breaking of inversion symmetry is at the heart of this response of a diode. Now, in superconducting analog of it, or superconducting Josephson junction,
how is it non-reciprocal? Because if I go from IV, I minus V, how would that be symmetric? Zener diodes are not symmetric.
No, normal diodes are not symmetric. For example, the normal, I don't know what normal is, but this is the response of a textbook case of a diode. Then the one that you're talking about is a Zener diode, which happens at the negative bias, you lead to a breakdown. But in this regime, if I say whatever, 2 volts, minus 2 and 2, there is a radical difference in the response. It's non-reciprocal. Yeah, okay. But it's fundamentally, it's because of inversion symmetry breaking. So what now people understand is that under certain conditions, breaking of inversion symmetry and time reversal symmetry, you can realize an analog of this, which is a non-reciprocal Josephson junction, where you have a superconducting switching current, which is one magnitude on one side and another magnitude on the other side. Okay, so this is called the Josephson diode. It's the phenomenology is sort of this, and people are trying to understand what it means in terms of the microscopic physics and what one can do with it. So we sort of got into this based on sort of a lot of activity in the community after some theory paper came out, which is which basically said if you have 2 layers of high temperature superconductor like disco and you rotate them by 45 degrees and you put them on top like this, so you have an order parameter of the upper layer which is blue and the order parameter of the lower layer is red, and now this will have no, if you just look at the geometry, there will be no supercurrent through this system because the two nodes are overlapping with the antinodes. Now, what they said is that if there is another process which is co-tunneling, so this co-tunneling of Cooper pairs, you can get what is called a topological superconductivity. This is all theoretical prediction. Tunneling of Cooper pairs gives rise to a topological superconductor which is at the interface. It will be time reversal symmetry broken, and it will last all the way up to 70 Kelvin or up to the TC of the system. But you have to twist the layers of the two superconductors close to the 45-degree angle. So this red region tells you how much you can band of twisting that you can tolerate, but still be able to get this topological superconductivity. So this was quite remarkable sort of prediction, and there was also debate whether all the aspects of it are correct. But since this was an interesting enough prediction, we sort of leapt into it, and that was sort of the genesis of our work, start of our work in twisted junctions of BISCO, which is twisting layers of BISCO by arbitrary angle and then trying to measure the Josephson junction that is formed. And so let me give you a flavor for the experimental part of it. Is that this BISCO crystal, is, as I told you, is already very finicky about oxygen stoichiometry. So what we did was, in our glove box here in the W sort of section of the lab, we had a glove box which is basically an argon with the ppm isolation of oxygen and moisture. There we have a microscope where the stage of the microscope can be cooled down to something close to minus 150 C. So this all we figured out on our own. Actually, Sanat, Vilas, and Amit, we said, okay, this is interesting. We have to figure out a solution. Over a matter of 2 months, we figured out a way to do it. And so we figured out a way to kind of take a crystal. If we want to know two arbitrary crystals twist by an angle, then we need to start from one mother crystal, peel off 2 copies, and then put them back together. That's sort of the strategy we use. So we start with a mother crystal. We peel it at very low temperatures, peel off a few layers of it, and assemble it to realize the overlap area, which is the Josephson junction. So it looks like this. So these 2 pieces have come from the same crystal, but they were peeled at very low temperatures, which ensures that the oxygen doesn't leak out. And then within a matter of a minute, you put them back so that now the interface is again buried. So these kind of experiments before this craziness of twisted 2D crystals were actually unimaginable. People never thought of them, but once people started doing it with graphene, people realized that you could do it with other things as well. So one thing led to another. So this is our device, and so the current flows here in plane in 2 dimension, and same thing in the dark blue. But when it goes from here to here, it actually flows perpendicular because it has nowhere else to go. And that's sort of the Josephson junction. So when we, this is sort of a cartoon. When we measured this kind of response of this device, we found a very large non-reciprocal response.
So we are using Scotch tape to peel it out and then rotate it and fix it like that.
It's analog or another name, it's a PDMS. It's a sticky polymer. We take a crystal, put that polymer, sticky polymer on top of the crystal and cool it down to the temperature I mentioned, something like minus 100 C. And then we pull it out. And that polymer grabs and picks out a set of layers inside the cryogenic state. Then we rotate it by the angle we want and put it back. Kept back immediately.
Kept back, but how to ensure that they are sticking together and the top part is removed again?
Oh, yeah, okay. So how does the glue come off? Is that so? It basically, the glass transition temperature of these polymers is well understood. So you use that when you put it back, put the second layer top, you rely on the grass transition. As you cross it, it's no longer sticky. So it just leaves that. Yeah. So these are some tricks from the community and some tricks we have figured out ourselves. Yeah. Lateral, okay, good question. Lateral displacement doesn't matter as long as there's translational symmetry of the lattice, which zeroth order is there. Rotation is sort of the key thing. Lateral translation will happen. Yeah, when you rotate by angles like 45 degrees or some strange angles, they're anyway not going to be a stable crystal structure. Here it's slightly much better than graphene. Where actually the layers will relax to minimize the energy. Here, because there's thicker layers, they are, so I hope I answered the question. So now the device looks like this, which is, I have one sheet of BISCO and another sheet of BISCO, and the overlap region, the current has to go through in the C-axis, perpendicular, and that's the Josephson junction. And so we measured the switching current, which is the current at which the Josephson junction switches from normal state to superconducting state, with another knob, which will become relevant in a minute, which is magnetic field, which is, if you notice this magnetic field scale, it's actually very, very small magnetic field. Earth's magnetic field is comparable to this scale bar that I have on x-axis. So we had to make a new kind of setup where we screen out Earth's magnetic field, and inside it, we made some homemade electromagnet to apply these controllably these kind of magnetic fields. Because the superconducting magnets have large enough trapped fields that you can't do these experiments easily. So we see that you can get this asymmetry in the switching current. And so the way you benchmark the asymmetry in, or non-reciprocal response is this parameter, asymmetry parameter, which is the difference. And that difference is actually tunable with magnetic field. That's sort of the interesting physics. And this effect is not one-off. You can measure it at variety of temperatures, variety of devices, which we had to measure to demonstrate. Right up to 77 Kelvin, you can see the asymmetry. And this asymmetry at lower temperatures can be as large as about 60%. So the asymmetry decreases with temperature. But one of the important hallmark of a Josephson junction is that, as I told you, that the switching is a stochastic event. For the same condition, if you switch it, try to switch it many, many times, it will switch at different current. And we systematically measured these histograms of switching. What we find is that the switching currents are asymmetric, which is I already told you about, but the histograms, which are different. That's telling us something deeper about the current phase relationship in this superconducting Josephson junction. And as we tune, the basic symmetry requires that if I flip current and I flip magnetic field, I should basically retrieve the original histogram. So if I have one sign of magnetic field, I see one distributions for switching, but if I flip it, I get back the original. So I plus and I and B, if they're both interchange, by symmetry arguments, you expect it to be the same. So, and this asymmetry is sort of somewhat detailed here, but what I want to tell you is it peaks at 45 degrees, which is sort of the angle at which these theorists predicted that you could get some interesting physics. At other angles, it's there, but it's actually suppressed quite a bit. So around the same sort of time, we were competing with another group who were also reporting these results. And they see similar phenomenology in their experimental results. This is a group of Philip Kim at Harvard. And they show a kind of diode-like behavior. And their paper came out about a month before ours in Science. So there is a sort of consistent response of the devices across certainly two groups. So now we also spend quite a bit of time trying to understand it. So I'm going to give you a kind of a very simplified version of that explanation. And there are still some loose ends, which I'm happy to talk more. So what happens in these kind of high temperature superconductors, there are two kinds of vortices. So when you apply a perpendicular magnetic field, you get vortices which are sort of the Abrikosov vortices that we know, and another vortex which is called the Josephson vortex. And that's because these high temperature superconductors have these copper oxide planes. Anytime the phase between two copper oxide plane moves, you have a motion of a Josephson vortex. But because of this material, if you apply a magnetic field and you twist them, what happens is that the two halves of the pancake vortices can get split up and you can get an in-plane Josephson vortex. And that is sort of central to this. I'm going to wrap up in a couple of minutes, actually. And the fact that there is an in-plane Josephson vortex is central to this observation of this Josephson diode non-reciprocal response. Another way to think of the non-reciprocal response is that if you think of the current phase relationship of a Josephson junction, like I told you, if there are higher order terms in the Joseph's current phase relationship, then switching from one side for one sign of tilting of this corrugated potential from one side and tilting from the other side can be quite different. And that arises from sort of complexity of this current phase relationship, particularly if there is a time reversal symmetry broken state at the interface as those theorists predicted, it could give rise to this non-reciprocal response reflected in the current phase relationship. So that's sort of the big picture. So there are some microscopic things that we are still kind of working on. So people have been looking at these for fundamental physics as well as technology. People have been looking at superconducting diode effect in a large variety of systems. And these are all, before our work, these were all at 4 Kelvin or less with asymmetries which are order of 10%. And when we sort of demonstrated and explained that we can see these asymmetries right up to liquid nitrogen temperature. So for cryogenics and application, liquid nitrogen is a kind of sort of an important temperature, because liquid nitrogen is technologically very easy to access. And we also showed that you can get very large asymmetries in these kind of systems. So what next? So we have already made, Amit has actually made squids, which are essentially two Josephson junctions in parallel with a loop in between. And that forms essentially the circuit is, and when you thread flux through this, for every quanta of flux that goes through it, you see an oscillation, and sort of that's what you see here. So it's one of the ways to measure magnetic field very sensitively. So these are at 77 Kelvin. And we are trying to understand some physics. There are also some interesting predictions for some unusual qubits using these high temperature superconductors and combination of S and D wave superconductors. And that's something that we're kind of have taken some steps to do experiments. That's sort of immediate future for us. I think that's all I wanted to talk about. So this is what I promised you. And I have more or less covered. Maybe I went over a couple of minutes, but I thank you very much for your attention.
Fantastic, fantastic colloquium with very nice illustrations from the work. So questions, open, yeah. First, we'll take students, yeah.
So you showed that the D-wave symmetry and the twist. So the role of the D-wave symmetry and the twist is ultimately to give the current a unidirectional form.
Yeah, the twisting basically, because the current that will go through the Josephson junction is in D wave, in the, sorry, C axis. And so if I have a D wave symmetry for the crystal, this crystal, and I have a rotated crystal, the symmetry is rotated by the same angle of real space twist. So that controls the Josephson junction's properties.
But-
and the non-reciprocal response is related to the angle of twist.
Okay, but when you are varying the twist angle, then you will also get in plane.
So we don't have a way to make one device and rotate it continuously. We make many devices with different twist angles, and we can in plane current. So we don't. So you're worried about if I have some junction like this. So the current here flows in plane, but here it has to go perpendicular to the c-axis. So you're worried about the current changing, or what was your concern?
So you showed a graph where you varied the twist angle apart from 45 degree to like 22 degrees and so on. So why you did that?
Why? Because we wanted to understand. So by twisting, a fundamental symmetry that we broke was inversion. Then we apply a magnetic field, so we break time reversal symmetry. We wanted to understand what is just breaking inversion symmetry at 45 degree enough, or 30 degree enough, or something more fundamental is happening because of the order parameter. So 45 degree, because of the D wave symmetry, has a peculiar meaning. Okay, does that answer your question?
Yeah, no, I'm thrilled by the detector part, but what is the detectivity that you estimate?
So
How many
far,
photons would be detected if 100 are incident?
so far, what we have characterized and benchmarked is responsivity. Maybe I can show you. The responsivity is like something like order of a few hundred amps per watt. Volt per watt, kind of.
No, so you can translate that into photons, no?
Yeah, so our work right now, we have not in this work, we have not demonstrated single photon. This is something that we want to improve the electronics and show, but immediately after our work was published, the MIT group has shown that it is a single photon detector.
Oh,
Yeah.
with what kind of sensitivity?
Uh,
The optics people fight for 96 to 99.
Okay, I'll have to. So, just to be clear, and there's no misunderstanding, we have demonstrated that we can detect photons, but we have ourselves not demonstrated single photon detectivity. Around the same time, MIT group showed. I'll have to look at their paper or share that paper with you. I don't remember that number off the
Because this
hand.
can change everything.
Yeah. Yeah. Thank you. Rita.
So then the Josephson diode thing, the principle of that.
Yeah. The mechanism, or what is the
Mechanism, how you are making.
Yeah. This part, or how we are making, I didn't hear you.
Hello, how it acts as a diode, diode like device.
Yeah, so if you look, one way to think about it is that easiest, quickly to explain is using this. Let me try to explain using that. Then otherwise, I'll also show. So when you have a simple Josephson junction, as I told you earlier, the switching of the Josephson junction means that you tilt, the more current you send through it, DC current, it tilts more. And at some point, it becomes like this. And at that point, it can either go by thermal activation, because it has to start sliding. And either, so let's stick to thermal activation. So if it slides, then you get a term which is phi dot, because x-axis is phase. Now, one way to think about the asymmetry is if there is another harmonic in like a cos 2 phi kind of term, which is sort of depicted here. And if my system sticks here and I tilt it, the potential that I have to overcome for the system to escape on one side is different from if I tilt it on the other side. And that is the genesis of the non-reciprocal response.
Point of inflation on the curve or some
Sorry?
point of inflation or something like that.
This is a local minima where the system
local.
can get trapped.
Okay.
Okay, and the more you tilt it, the more current you send, the more you tilt it. So either it will switch by thermal activation or quantum mechanical tunneling, whichever are the mechanisms there. In our case, you don't really need quantum mechanical tunneling at the temperatures, you just need thermal activation.
More questions? Let's talk to Mandar in a relaxed atmosphere of having some snacks. So thank you all for joining. And thanks, Mandar, for a wonderful colloquium. And thank the YouTube people for joining as well. I would also want to thank the AV staff in AG66. So thank you.
They're shaping it into a nanowire. The chromium